So I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. So today we are going to see in lecture number 5 one-dimensional steady state conduction equation. So for getting this we have to first understand how the three-dimensional heat transfer will take place, and after that we will derive or we will simplify the three-dimensional equation to the one-dimensional equation. As before in some lectures I have taught you that the state or steady state or transient state, also the conduction, convection and radiation. So basically we will brush up your things. So basically there are three modes of heat transfer. First is a conduction, second is a convection, and third is a radiation. So conduction happens due to the solid state, or conduction happens in a solid state because of vibrational energy and the free electrons of the molecules or atoms. Okay, so for steady state the equation will be, or the steady state, the properties will not be going to change with respect to time. So let's start the today's lecture. So again we are brushing up some ideas about conduction. So what is mean by heat conduction? The transfer of thermal energy within the material without a material movement. The molecules and atoms are going to vibrate, but material movement is not going to be happen. When the material movement or the fluid movement or the flow of the fluid will going to happen, then we will see the convection type of heat transfer. Okay, so occurs due to the molecular vibration. As I said earlier, the conduction is occurs due to the molecular vibration and the free electron movements within the material. Okay, so material is not going to change, or material, the movement of the material will not going to happen, but inside the material at molecular level the vibrations are going to happen. Also due to the free electron movements the heat transfer will going to occur, and that heat transfer is nothing but the conduction heat transfer. Okay, and as in last lecture we have seen that it is described by the Fourier law, where the Q is heat flux, which is heat per unit area, is equal to minus K dt by dx, where K is the thermal conductivity and dt by dx is a temperature gradient. Okay, so heat conduction in three-dimensional. So today's lecture topic is a one-dimensional steady state equation for conduction, but we are going to see a heat conduction in 3D. And why it is so? Because in general or in real life all objects or all real materials or any engineering applications will have three-dimensional heat transfer. But for our convenience we are going to see it in one-dimensional. But for analyzing the heat transfer in one-dimensional, you have to understand how the heat transfer will take place in three-dimensional. So that's why we are here seeing that the heat conduction in three-dimensional, when you learn this heat conduction in three-dimensional, then it will be easier to you to analyze or to apply the basic things for one-dimensional easily. Okay, so heat can flow in x, y and z direction simultaneously. So let's take an example of a metal rod. Okay, so let's take an example. Let's consider this is a metal rod. Okay, if we heat this rod from one end, okay, the heat will going to transfer from this end to this end. Okay, as you know, because there is a temperature difference is there, and with respect to this distance, which is called as a temperature gradient. So the temperature gradient is acting on this metal rod. Okay, so just right now it consider it is a metal rod. Okay, this is a metal rod, and if we are going to heat this rod from this end, due to the temperature gradient, which is the temperature difference across this length, the heat will going to be transferred from this end to this end. Okay, so by that just you can see that this metal rod is having this breadth, okay, this length and some thickness. So these are the three dimensions. When I am going to heat this metal rod at one end, then but obviously the heat will be transferred with these all dimensions likewise in the breadth size, length size and thickness size. Okay, but we in Fourier law we have just seen that we are considering only the length of that metal rod, okay, or the thickness of that metal rod. But in actual practices, the heat is always going to transfer in all directions. So that's why the figure illustrated here, you can see that. So the heat conduction in 3-dimensional is used for realistic geometry. So in actual practices, the heat is always going to transfer in all 3 dimensions, okay, and it is a time dependent problem. Also the time also dependent. We have seen in last lecture the steady state and transient state. In steady state, the material properties are not going to, or heat or energy is not going to transfer or change with respect to time, okay, and in transient the heat or a temperature is going to be changed with respect to time, okay. So in realistic, the all 3 dimensions are necessary, and in all 3 dimensions the heat transfer will take place, okay. For our convenience, we are converting that 3-dimensional thing to 1-dimensional for convenience of our analysis of the things, okay. So consider this block, consider this metal block. If let's say this direction is x-axis direction, okay, so this block having in this direction delta x is a thickness, okay, here delta x is a thickness. Then after this delta x thickness, whatever the heat is going to be conducted out from this block is qx plus delta x, okay. So qx amount of heat energy will going to enter in this block, but after this delta x distance, the heat energy which is coming out from this block is, we are denoting as qx plus dx. So similarly in y direction, here you can see this, here delta y is the thickness in y direction, okay. So when the qy, that is heat input with in heat input in y direction is qy, but after this delta q thickness, the heat output is qy plus dy. Similarly in z direction, this is the z direction, okay, so this thickness is delta z, okay. So similarly in z direction, qz is a heat which is input in this block, okay, but output is qz plus dz. So have you understand this thing? Likewise, let's say this metal block, okay, qx is a heat input in one direction or in x direction, then this length is a delta x, so heat output is qx plus dx. In y direction, the heat input is qy and output is qy plus delta y. Delta y is a thickness in y direction. Similarly in z direction, let's say in z direction, so qz, if it is input in heat, so this thickness in z direction is delta z, okay, here we can see that. So qz is the input, then with delta z as a thickness, so output will be, or output heat energy will be the qz plus dz. You have just understand that how the heat transfer will take place in x, y and z direction with the thickness, okay. So purpose of this 3-dimensional equation is that we can predict the temperature variation over the time and the space, okay. In 1-dimensional, we are going to observe only a 1-dimensional heat transfer, that means only length, only in the length direction, or only breadth direction, or only the thickness direction, okay. So 3-dimensional heat equation will works in Cartesian coordinates, cylindrical coordinate as this has been shown, and spherical also. So in cylindrical coordinate system, the heat can be transferred in axial direction, that is the first dimension, in radial direction, that is the second direction, and in angular direction, this is the axial direction, and in angular direction also, that is one third dimension. Similarly in sphere also, okay. So how the three-dimensional heat equation can be calculated? Before just we have seen this, how these equations, before this we have just seen that how the heat is going to transfer within x axis, within y axis, and with the z axis, okay, and with the z axis, okay. So these type of three types or three directions of heat will going to be conclude in the equation likewise in this equation. So this is the three-dimensional heat equation, okay. So temperature difference across x-axis, temperature difference across y-axis, and temperature across z-axis will going to be concluded in the three-dimensional heat equation. And this is the property, or this is the internal heat generation component. This is the internal heat generation component. What is mean by that, we are going to see in this next slide, okay. And this is a time variant factor. And what is the time variant factor? That is also we are going to see in the next slide, okay. So just now right now the derivation is not necessary here. As for this course, you are going to see the detailed derivation in your core course as a heat transfer as a main course in a third year. But right now, what are the relevance or what are the factors are here in a three-dimensional equation. You have to just understand this thing. So this is a x directional component of a three-dimensional heat conduction equation. So this is a y directional component, this is a z directional component, this is the internal heat generation component, and this is a time variant component. And what is the relevance of these, that is I am going to see show you in next slide. So in general heat conduction equation, this is a x directional temperature term, okay. This is a y directional temperature term, and this is a z directional temperature term, which are we have seen that in this diagram. So this q dot by k is an internal heat generation. So what is mean by that? So let's again take a help of this highlighter as a metal rod. So let's consider this metal rod of a steel, okay, is contained a uranium molecule inside it, okay. And if you are know that the uranium has its property as a radioactive material, it will generate some amount of heat within which is its material property. So let's say one kind of radioactive substance or some internal heat generation component is placed inside this metal rod. Then while conducting the heat from this end to this end, okay, normally if there is a no internal heat generation component, means radioactive material or any other external source, okay, if it is not present, then normally the heat is going to be transferred from this end to this end, okay, this end to this end. But if when the internal heat generation component is there due to the material property of certain materials, then the heat is going to be transferred, but in another way, okay, in not in a same linear graph. Whatever we seen in a second lecture, the temperature gradient graph is a linear, but due to the internal heat generation component, that graph will not be at a linear direction. So it will be elliptical in the sense, and that is a more some complicated thing, but it is simplified in your core subject. Right now you have just understand that with the internal heat generation component, the material due to the material property, the heat transfer will going to change in certain direction, okay. Again, this second term is a time dependent term. So what is mean by this time dependent term and what is mean by alpha, I am going to elaborate right now. So here the term time dependent is used for steady state or a transient state. So what is the relevance of this time dependent term? As we have seen in the last lecture, what is a steady state conduction or a steady state heat transfer or a transient state? So let's take an example of this metal rod. So if let's say consider if this metal rod is at a 60 degree Celsius, okay, and I am at a room temperature. So this state of this metal rod and myself will not going to change after 10 hours. So if this condition will occur, then it is called as a steady state. What I mean to say is that, let's say at 10 a.m. this metal rod is having 60 degrees Celsius and myself is at a atmospheric temperature, okay, and after 10 a.m., let's say after 6 hours later, let's say at 4 p.m., this state is remains same, means this metal rod is having 60 degrees Celsius temperature and myself holding this metal rod also having same atmospheric temperature. Then the state is called as a steady state, where this term will become zero. So change in a temperature with respect to time, if it is zero, then it is a steady state condition, okay. And but in normal life, this will not happen, okay. So let's consider an example of you are holding a cup of tea at a mountain or at a hill station, okay. If you are holding a tea at a mountain and the tea initially is having temperature of 40 degrees Celsius and you are holding at let's say minus 10 degrees Celsius surrounding temperature, after 1 hour the tea will lose some heat, okay, and the tea will get cools, okay. After let's say 1 hour the tea will get cools, okay, and your body temperature will also match to the surrounding. So at that time the initial temperature of the tea is more, but after 1 hour the temperature of tea will be less, okay. So that is the change of temperature with respect to time at the hill station of your tea, okay, is changing. So that's why this case is not considered as a steady. This case is considered as a transient transient conduction or transient state, okay. So transient state means what? The temperature is going to change with respect to time, okay. If after some time the temperature is always going to change. In actual practices, the transient conduction, convection or radiation is only the possibility, but for simplification we are considering a steady state, means temperature of that object or of a metal rod or of a cup of tea is not going to change, okay, because to simplify the analysis, okay. This lecture is concerned, this lecture's title as a one-dimensional steady state conduction equation. So as before I have said that in a steady state the time variation is equal to be zero, okay. So in steady state the time variation for heat transfer is equal to be zero, and for transient term this term will be present. So for steady state this term will be equal to zero, okay. So as far as this equation is concerned, this is a x directional temperature term, this is a y directional temperature term, this is z directional temperature term, this is internal heat generation term, and this is time dependent term for three-dimensional general heat conduction equation. So simplification scenario, as I have stated before starting this lecture, that we are going to see how the three-dimensional heat transfer will going to occur, or how the three-dimensional equation is going to occur in normal scenario or real world, and from that three-dimensional equation we are going to derive or we are going to simplify it for one-dimensional steady state heat conduction equation, okay. So for steady state, as I have stated earlier, remove the time term before. So for steady state this term is equal to 0, okay. Then no heat generation, then remove q dash. So if there is a no internal heat generation component or there is a no radioactive material present, then this term will also become 0, okay. Then for constant K, the K comes out of derivative. So here for one material, the thermal conductivity of steel, let's say this once again we are using this steel bar. So for steel bar, the thermal conductivity at this point and the thermal conductivity at this point and thermal conductivity at this end will not going to change. Okay, if there is another material attached to this, then the thermal conductivity will be going to change. Okay, so right now the thermal conductivity of steel is everywhere same. Okay, so this thermal conductivity we are keeping aside this XYZ term. Okay, and for two dimensional and one dimensional simplification as per the geometry, what is need to see here, for two dimensional there are two components of dimension. Okay, so only we are considering two components of dimension, third component is 0. And for one dimensional we are considering only one dimension. Simple is that. Okay, so for one dimensional we are considering only one dimension, so other two dimensions will become 0. Simple is that. Okay, so once again I will repeat. So this is a three-dimensional generalized heat conduction equation. In these are the temperature terms in x direction, this is temperature term in y direction, this is temperature term in z direction. Okay, q dot divided by k is the internal heat generation component, and 1 upon alpha dou t divided by dou tau is equal to, that is a time term in this general heat conduction equation. But as far as a steady state concerned, this term will become 0. Okay, if there is a no internal heat generation, then this term will also become 0, and this is a three-dimensional equation. Okay, this is a three-dimensional equation. So to convert this three-dimensional to two dimension and one dimension, we are just considering only for two-dimensional equation we are just considering two dimensions, and for one dimensional equation we are just considering one dimension, so other dimensions will become 0. So let's say for two dimensional equation of heat conduction, this will become 0 if it is not if there is a no internal heat generation, then this will become 0, and if there is a steady state, then this will become 0. So two dimensional steady state internal heat generation, two dimensional steady state without internal heat generation, then this equation will become dou square t divided by dou x square plus dou square t divided by dou y square is equal to 0. Simple is that. Okay, and for one dimensional steady state, no internal heat generation, this equation will become, this is equal to 0, no internal heat generation, then this term will become 0. For steady state, this term will become 0, and only one dimensional is present there, so other two dimension will become 0. So dou square t divided by dou x square is equal to 0. This is a one dimensional steady state without internal heat generation equation. Simple is that. Okay, so we are here simplifying the three-dimensional equation to one-dimensional equation or two-dimensional equation. Okay, so whatever I just said here, it is represented similarly. So one-dimensional steady state conduction equation in only x direction, we can, and with a no internal heat generation equation, d square t divided by dx square equal to 0. Okay, so what is the relevance of this equation and what is the use of this equation in our general life? That is what we are going to see in further. So this special case or a one-dimensional case with no internal heat generation, Okay, so Q dot divided by K term will become 0. So further simplified to the linear temperature distribution, what is meant to see here, only we are considering this dimension, only one dimension. Okay, so in this dimension, as we have seen in a Fourier law, we are seeing that same, the Fourier law is applied, or Fourier law is similar to the one dimensional heat conduction equation. Okay, difference is that here we are generalize the thing, and in Fourier law we are just keeping it in a standard or empirical format. Okay, so generalized state of one dimensional heat conduction equation, as we have derived, okay, dou square T divided by dou x square. If we double integrate this, then we will have the temperature term, okay, in some constant. And if we apply the boundary condition, where T1 is a boundary condition, T2 is a boundary condition, and Tx, okay, is a middle condition, then we will get this equation, and this equation will help us to understand how the temperature is going to change linearly in between. What I mean to say is, if we know that the temperature of one side and temperature of another side, and if we want to find the temperature in between, how much is the temperature, then this equation will helps us only in one dimensional. Only, don't forget this one dimension. Okay, in two dimension this equation will be another type, but for only in one dimensional equation, if we know one temperature of one side and another temperature of other side, and we will have to find the between temperature, then this equation will help us. So see this equation, Tx is a temperature where we have to find the temperature at certain distance x, only in one dimension. Okay, here we are considering only x direction. Okay, only x direction we have considering. So T1 is a boundary temperature in at a one side, let's say at a hotter side, and T2 is a boundary temperature at a colder side. Okay, so Tx minus T1 divided by T2 minus T1 is equal to x divided by L. X is a distance where we have to find the intermediate or in between temperature. Okay, and L is a total length or total thickness or total whatever dimension in x direction. Okay, so simple is that. So Tx minus T1 divided by T2 minus T1 is equal to x by L. If you have normal numerical problem, so L is given, x is given, and you have to find that Tx and T1 and T2 are given. So it is just simply mathematical term to calculate cross multiplication, and you will find the intermediate temperature. Okay, so application of this equation. So where it is used? So in first starting of this lecture, I have said that the three-dimensional heat conduction equation, actually it is a realistic equation of heat transfer that is used in everyday life. Okay, but to assume or to simplify the things in one dimensional, to analyze how the heat transfer takes place in one dimensional, we have converted that three-dimensional equation to one dimensional equation. So the heat exchanger, earth crust analysis, and then building heat losses as insulation or without insulation, then turbine blade cooling, laser tissue interaction, these are the applications where we can use the three-dimensional equation, but to understand how the heat transfer takes place initially, we are converting the three-dimensional equation to one dimensional, because it is much easier. Okay, here you can see that it is much easier to understand how the temperature are going to vary with this length. Okay, I can put this x with some other x plus dx. Okay, and I can find this temperature at this temperature at this x plus dx, what is the temperature here also, by putting some terms here. Okay, so one dimensional analysis of heat transfer will be much easier. So that's why these applications are actually three-dimensional heat conduction equation, but we are converting it to one dimensional for easierness. Okay, so summary of key learnings. So one dimensional heat conduction equation helps us to analyze a basic profile, how the temperature is going to change. with the one direction. Okay, and three-dimensional models solve the complex problem with a geometry and the time. So three-dimensional problems are the realistic and more complicated problems, but before going to these complicated problems, we have to see the basic things. So that's why the one-dimensional equation will help us to analyze the basic things. So what is the importance of this? Understanding the conduction is a key to the effective thermal system design. So while understanding the one-dimensional heat transfer or a three-dimensional heat transfer or a two-dimensional heat transfer, it is a basic need to understand how the thermal system and how the thermal system to be designed. Okay, you can't design a thermal system without having known that how much heat we have to transfer or how much heat transfer we have to control it. Okay, so it is used in the mechanical, civil, aerospace, biomedical engineering. So vast application of heat transfer is there. So thank you very much. So for this lecture we have seen that how three-dimensional heat transfer equation is derived with a metal block having x direction, y directional and z directional temperature profile with the internal heat generation, and how the time term is there, and the time term is absoluted or time term is equal to 0 in a steady state. So this three-dimensional equation we have converted to one-dimension equation, and that one-dimensional equation we have again converted to find the temperature profile at x distance. So that's all for this lecture. If you have any doubts and queries, you can find me in a discussion forum in the comments box. So feel free to ask me anything. Also, the total introduction to the heat transfer, a practical oriented approach, I will publish this book on this online platform, and you can find it in a discussion box. So thank you very much.